speaker, Nikolaj. So he comes from Denmark, so kind of a neighbor. And we just found out that his package, the one he's going to present right now, initially I started at your PhD studies, at your studies, university studies. But I usually say like, oh, well, after the university, students just leave their packages and to rot. But he keeps alive, so I'm very happy with that. So please welcome our speaker, and he's going to talk about his package.
Thanks a lot for coming, and I would like to talk about my package called RayTraceHeatTransfer, which models 2D enclosure radiative heat transfer. And the slides you can see on this link if you have your computer. And this is the agenda. What I'm going to talk about, I have structured it as a series of questions. First, I will talk about what is this package for, and why this package, and then what does it solve, which limitations does it have, how does the meshing work, how does ray tracing work, how does the heat transfer calculation work, and the future of this package, and then just the last slide about why I use Julia for this. And these two pictures were generated with the package. It's generally where you can see that the top picture is there's some random noise because I only ray traced a few rays, and in the last picture there's much more coherence, or what to say. Then what is RayTraceHeatTransfer.jl for? It is for it's a Julia package for 2D radiative heat transfer calculations in participating media in custom geometries. And then I want to define what some of these terms mean, because it might not be obvious to everybody what it means. What is radiation in this? In this situation, it is electromagnetic waves, or you can also see it as photons, and that's mainly what I do in this package. Then what is heat transfer? Heat transfer is net exchange of energy due to a temperature difference. Then what is a participating medium? A participating medium is a substance between two walls, for example, that exchange energy through radiation, and then this participating medium, it interferes with that, and that's in the image there. It's the participating medium that I have graphed, and a hot lower wall and a cold top and side walls. Then the temperature distribution becomes like that. And my package can make custom geometries, and it doesn't have to be like squares. You can have skewed things also. But why RayTraceHeatTransfer.jl? It is relevant to, for example, combustion. That was my original motivation, but it is also relevant to climate sciences and astrophysics, where you also have some kind of gases that absorb and emit and scatter the radiation. So that's, Then what does RayTraceHeatTransfer.jl solve? It solves the radiative transfer equation. I didn't show the equation here because it's a long integro-differential equation, and then I had to explain all the terms. I would rather explain the phenomenon that it models, and it's an energy balance along a line of sight in any domain. Then we have some incident radiation and some transmitted radiation. And this equation models on a differential level what happens to the ray from it goes into that differential volume so it goes out. So then you have to integrate it along the ray. But the thing that makes it complicated is that all possible paths for the rays, they are coupled. So that's why it's an integral equation. And it's incredibly hard to solve, at least for general domains. And some limitations of my package. It cannot yet solve 3D problems, but I have some ideas on how to do that. It cannot solve the full spectrum, and it has some limitations due to the matrix formulations that it uses. The size of the matrices, they basically scale with the n square of the number of elements in your domain, so they can become very large. I'm thinking about using memory mapping to have the matrices on the disk and then allowing for larger matrices, but I'm looking into that. It's also not yet implemented for the GPU. Then how does it work? The package, first we mesh, and we build it from we build it like modularly, where we build it from convex quadrilaterals, and we just build one at a time, and then we plot it and then add another one, and each time we specify if the boundaries are solid, if they are impenetrable, or if they are open. So we can actually build something like a very complex domain from these definitions. And the reason they have to be convex is that then they are easy to ray trace. And then we generate the mesh by specifying the number of splits in each direction. And as I said, they can also be skewed in any way, basically. And then I showed here some ray tracing. I know it looks very chaotic, but it's a single function that samples and traces the entire geometry, and then the results of the ray tracing, they are stored in matrices, where each row in the matrix describes the probability from emitter I, from radiation emitted from emitter I, going to column J. So that's why we have for each row we have J elements, where one for each element in the domain. And in this picture, I think I traced what? Okay, I traced 2 per emitter, and in general I trace millions to get accurate results. Then lastly, the heat transfer works by using the matrices to do heat transfer calculations. Some things that I want to add to the package is a new matrix method, 3D domains, GPU-based ray tracing, spectral support, non-uniform gas properties, and time-dependent problems. And then lastly, why do I use Julia for this? Because this is my ray tracing. This is just pseudocode that I wrote to simplify it. But as you can see, there's a parallel for loop. Then there are 3 nested while loops. And this is basically one model set. So it needs to be very fast, especially if you have to trace 100 million rays or a billion. But in general, intuitive syntax, great packages, excellent linear algebra. And for ray tracing, it's important with the fine-grained control, excellent speed, and parallel programming. Yeah, thank you for listening.
Yeah, I think we had time for like 2 questions. So.
Okay.
Thank you very much for a wonderful talk. You mentioned that you use convexity to simplify the ray tracing.
Yeah.
Why is that? Can you do also non-convex domains, or what is required in your current implementation to do also non-convex domains? How much code will require to also be able to treat more general geometries? Thank you very much.
Yeah. Thank you for your question. I can easily do non-convex domains. I just have each element in the total domain has to be convex, because when it's convex, I can do like for these. They have like 4 sides. In general, I ray trace in each. I call them sub-enclosures. I ray trace each sub-enclosure. It only has like 4 sides, so I have to do like a function that calculates along a line which wall do we hit if we go along this line, and then I calculate if we go a certain distance, did we hit the line. And then actually when I ray trace only on the coarse domain, so to say, and then I find out if there's an interaction point where I basically map that to the fine domain. Okay. But I can easily do non-convex domains. Yeah.
Okay. In time, I think we have to wrap up. But once more, we thank our speaker.